Today's topic is magnetic field at the center of a toroid. Magnetic field or magnetic field intensity due to a toroid. So what is a toroid? What is a toroid? A solenoid in the form of a coil or ring, in the form of a ring, is called a toroid. So if you look at this, so this is our solenoid, okay, and if I make it in the form of a ring, so it would be something like this. If you make it in the form of a ring, circle, right, that is a toroid, okay, but this is not the actual picture. So for a toroid, so in case of toroid, B, magnetic field exists only inside the toroid, okay, and it exists only inside the toroid, and there is no magnetic field. There is no magnetic field outside. Okay. V is very strong and uniform. B is very strong and uniform inside the toroid. So what do I mean is this? So imagine I am going to draw now. Now this toroid, I'll show you a toroid. Toroid B. See, they are showing me different images. Yeah, here is the toroid. This is a toroid. Okay, so this is a toroid. So then, so for a toroid, you can see that means the magnetic field lines are like this way. So if you cut it, you're going to, so you can see the magnetic field lines start like this way. Okay. This is the toroid, right? Now this is the current. This is how the current is going. This is the radius of the toroid. If I take, this is the center of the toroid. This is the radius R of the toroid. The magnetic field exists only here. These circles you see, these magnetic field exist only here in the form of concentric loops like this, not intersecting, not disturbing each other, they stay in the form of
loops.
Now in order to find this, so definitely we'll start by considering one. We'll consider one. Let us consider a toroid. Consider a toroid, ID toroid of radius, means it has two radius, the inner radius, okay, that ring radius, the toroid of radius r, okay, and this being the thickness, we're not interested in the thickness. So toroid of radius r carrying current I has n number of turns, okay, has n number of turns, and yeah, this is it, n number of turns. So now what we're going to do, we'll draw one more diagram. This time what we're going to do, we're going to cut this. We're going to cut this into I'm going to cut it. See, I'm going to cut it now. So if I cut it, the current, look at this current, how the current is going. It is coming from here and going in, no? So from here it is coming and going in.
Yes, sir.
So I will show some dots here. Circle, circle, sorry, and here also. Okay, so like this I cut it. So here I'll put a dot because current is coming out. Okay, so dots. Okay, I'll put a dot there. And I'll put a cross. Means getting in, no? That means I have cut it from the. So I've cut it. Okay. So the rod has been cut. Now what you do? The toroid has been cut. As it has been cut, what do I get here? And then I will define one imaginary circle. Imaginary loop known as the Gaussian loop. Okay, so this is the Amperian loop. I can show you one more side diagram. That means if this is the loop, you can see this is how the current is entering. No? This is how current I is entering. Because from here the current is starting and then again it is going in. I have cut it into two halves. This toroid has been cut into two halves. from the center. Okay, right or not?
Yes, sir.
Then to find B at the center, we draw an Amperian loop in the form of a circle of radius r. Okay, of radius r. Now that means you see here also I've taken this as AR only, but actually we should draw, let me take this A, not R, of radius A. Let this be A. Okay, then it will be radius A, this is A. You'll see why. So we can find out magnetic field in 3 regions. One will be, actually let us draw this. Now when so these are L1, let me draw two more loop. One will be here, one will be here. This is also R. So this is, let me name this L1. Let's say this is L2, and the another one is there which is outside. Okay, another one is there which is outside. So there are 3 loops we have drawn. Clear?
Yes, sir.
So now what are you going to do now? So let us to find B at the center, we draw an Amperian loop in the form of circle of radius r in 3 regions. In 3 regions as shown, right? So for the loop L1, close integral B dot dl is equals to 0. Why? As the loop L1 do not encloses any current. Encloses any current I, right?
Yes.
Do not. This loop, does it has any current?
No,
Within
sir.
it no current. So B dot dl equal to 0. What about L2? This is L1. This is L1. This is L2. This is L3. What about L3? What about L3? There is no magnetic field outside. There is no magnetic field outside, right? If you look here, the current coming out and going in same only
Yes.
for this loop. Okay. For L2, for L3 actually, for L3 again B dot dl equals to 0, right? But for L2, what you can do, we can define a dl. This is our dl, okay, at a distance r, right? This is r. The direction of dl is, the direction of this length vector is tangent to this point, okay? Direction of magnetic field is also tangent to this point, correct? For L2, the direction of the direction of dl vector and b vector are what? Parallel. Okay, that is tangent, that is along the tangent at any point P. Any point P. Therefore, what can I write? Close integral b dot dl would be equal to close integral b dl cos 0, right? Because the angle between dl vector and b vector is 0 degree. Am I right? Right? You
Yes,
got
sir.
it now? So then
Yes, sir.
0. Therefore, I get here what? I get here close integral b, this is the line integral b dot dl will be equals to mu naught I. Isn't this ACL? Okay, so I can write using Ampere's circuital law, I can write this. So b would be now equals to dl mu naught I. So if I integrate all the dl elements over this loop, over this closed curve, I should get here how much? 2 pi radius.
2 pi.
So 2 pi a will be equals to mu naught I. Okay,
2 pi.
a.
A.
So b equal to now mu naught I by 2 pi a. So for now, generally coil will have a large number of turns, is it or not? So
Yes, sir.
for turns, for n turns, okay, what should I get? B will be equals to mu naught Ni by 2 pi a, or I can write B equal to mu naught Ni. What is N? Where N is equal to number of turns by 2 pi a, means perimeter. Okay, number of turns per unit length. That's it. For number of turns per unit length. Number of turns per unit length. So remember, in case of solenoid it was N by L, and in this case it is
Yes.
what? In this case it is what?
Number of turns per unit length.
Here also same thing. That was only L. In case of solenoid it is N by L. It is N by L. But in this case it is N by 2 pi A.
2
Means
pi.
perimeter, because it's a circle. Okay?
Yes, sir.
Make clean it?
Yes, sir.
So let's go to. So these are the two applications of Ampere's circuital law. Now to understand Ampere's circuital law, we can do it another way. We can see. So let's just take one question here. Imagine this is a copper conductor. Okay. This is a conductor. Got it?
Yes.
The question says, find the variation of, give the variation of current, give the variation of magnetic field. Okay? Give the variation of magnetic field. Give the variation of magnetic field starting from its center. Starting from center
Center
to
to
starting from its center to any region, to any point outside the wire. To any point outside the wire. Outside the wire. Okay?
Yes, sir.
If A is the radius of the wire. If A is the radius of the wire. And J is the current density in the wire.
J.
Is the current density in the wire. So this is a conceptual problem. I'll draw the loop, the cross section in a very big circle so that we can understand one at a time what we mean here. So this is our wire. What I'm going to do now, I'm going to draw loops. So there are practically three regions. I will draw the Amperian loop. Here one, this is my L1. When radius of the loop R is less than A, right? Correct or not?
Yes, sir.
Please try to understand. I need to find, we need to plot a graph which will give you the variation of magnetic field starting from the center of the wire to the region outside. Clear?
Yes, sir.
That is the idea. So now what I can do is this. So first of all, for R, what is R? R is the radius of the Amperian loop. R is less than A. We know line integral will be B dot dl into mu I. Mu into I. Right? So in this case, I. What is I? But wait, okay, let us not do this one first. You are not going to understand this. Let R is greater than A. Means I am talking about any region outside. So here is my Amperian loop, which is outside the conductor. So I am talking about any point outside. It is indirectly saying what is the magnetic field outside the wire. Okay. So here this is R. Clear? R is greater than B dot dl. So in this case, if I do this, is what do you think? Isn't this the magnetic field due to a wire? Magnetic field at the what? This is B due to a straight conductor outside. No, we have already derived it. Because if I do B dl mu naught I, correct?
Yes, sir.
And then this is going to give me B equals to 2 pi R, simple, mu naught I. I'm going to get this, so B will be equals to mu naught I by 2 pi R. Very good. This is B outside. Are you getting my logic?
Yes, sir.
Now for R equals to A, same thing. So you can notice here one thing, B is inversely proportional to R. Radius.
Yes, sir.
Everything else is constant. Right?
Yes, sir.
Now, so what I can do now here, now what to do? In case for R equals to A, same thing. But what? Same thing. So B on the surface, so I'm just writing BS, will be again same thing only, mu naught I, because same current is there, mu naught I by 2 pi R only. Okay, that means I need to draw a Amperian loop with just over is on the surface. Correct?
2 pi R.
Are you getting the logic, what I was explaining you here?
Yes, sir.
Now what about the inside? For R less than A, now the current is not same. J would be equals to what now? J would be now, current density is even the same, I1 by area. So you yeah. So because I is the total current through the wire, and I1 will be only current through
the first loop.
only the loop, that much of radius, how much I have done. This is I1, na? So that
Yes,
means
sir.
I1 can be written as J into area 1, or I can write this J into pi R1 square. Right?
Yes, sir.
Pi R1 square. Therefore B dot dl, if I do, correct?
Yeah,
Now if I do this, I get this at 2 pi R.
d2 pi is equal to
This is R1, R1 square. So R1 cancel. Okay, let the pi be whatever be there, both those things are constant. That is not my concern here. So here it is mu naught j pi
pi.
by 2 pi into r. So giving everything, what you see here, b is directly proportional to r. So if I plot the graph, this is the answer. So if I plot the graph, I will see that the magnetic field is directly proportional to r. So it increases, varies. B, this is r, it directly proportional, so increases gradually linearly, because any directly proportional is a straight line, and then it reaches to the maximum value, which is at the where radius, and then it drops because inversely proportional.
So it'll come down gradually.
It will never meet the axis, but it will go like this.
Infinity.
Infinity. P proportional to 1 by r, B directly proportional to r. Interesting, right? So magnetic field, that means, this proves also one more thing. Magnetic field do exist inside the wire.
So if this is magnetic field when inside the wire, then 1 minute, just give me 1 second.
There's something called Hall effect.
So I'm slightly confused between just now the toroid that we did, and then we
That is,
took
toroid is something what you have seen in the toroid, that there are coils. Within the coil the magnetic field exists.
Yes, sir.
Within
This is just a wire.
This is within the wire, within this solid.
Achha. Yes, sir.
Okay. So this is a very interesting question. May I clean it?
Yes, sir.
Now let us come to Lorentz force. What is Lorentz force? In case of Lorentz force, so any charged particle, moving with the velocity v, when it enters a magnetic field, it experiences a force perpendicular to the, it is a force in a direction perpendicular to the direction perpendicular to the magnetic field, perpendicular to the plane of B and V. Okay? This force is known as Lorentz magnetic force, and given as, this force is known as Lorentz magnetic force. Fm is equals to BQV sine theta, or we can write this as Fm is equals to Q V cross B, cross vector. Again it's a cross. That means, what are they saying? That imagine this is a magnetic field going like this way, and this is any charged particle which is entering the magnetic field, which is entering the magnetic field, correct, with certain velocity v. That means this is the velocity vector, this is the b vector. So b cross b, v cross b, that means the particle will experience a force which will be directed downward. And if it was entering from this side, and if another charged particle is entering the magnetic field this way, there's another plus particle. We'll see that plus q and minus q. So then the force will be, so this is v, this is v, it will be upward. Then the force will be, this is the velocity vector and this is the magnetic field vector. So you can see v cross b, so it will go up. This is the force, this is Lorentz magnetic force, or v cross b, b q v sine theta, or Fm equal to q v cross b. This is the vector notation, and this is the notation. That is this magnitude of b q v sine theta, where theta is what? Where theta is the angle, equals to angle between velocity vector and the magnetic field vector. Magnetic field vector. Okay.
Where theta is
angle between velocity vector and magnetic field vector. Clear?
Yes, sir.
So the direction is given by right hand rule.
Yes, right hand.
The direction of this force is given by, as you have done this earlier also, the right hand rule. Or no, direction of this one is given by the right hand rule by using the cross product, but then we can also use the left hand rule, Fleming's left hand rule, to explain this. Force, field, no, not now, that is in a different, sorry, what I am saying. Yeah, we can use the right hand rule to find out. That means the one which I have already taught you, that you align the right hand with the velocity vector, and then gradually fold it toward the magnetic field vector. The thumb will give you the direction of the force. Okay. Now it may happen. Now it may happen that a region contains both electric field and magnetic field.
Yes.
And magnetic field, as shown. So if this is the plate, okay, and here is a charged particle which is coming towards this way, and the cross products, this cross represent that the magnetic field is going into the plane of the paper, right? So in this case, the force experience by because electric field is also present. Electric field is from like this to this. This is plus, this is plus, this is minus. So that means electric field lines are like this way. Okay. So in this case, what will happen? The charged particle, now can you give me the direction? This is velocity v. Both electric and magnetic field, both of them are present. Both of them are present. Now for the charged particle to go through, we'll come to that. To go through undeflected, we'll come to that very soon. But in this case, the total force experience would be, will be, F will be equals to the electrostatic force plus the Lorentz magnetic force. So which I can write this as Q into E, which is the electric field vector, plus Q into V vector cross V vector. Right? So that means this force, these two together, we'll call it as Lorentz force.
Okay.
That is also called Lorentz force, but This collectively, when a region contains both, then we can term this also as the Lorentz force. Okay?
So will we see deflection?
Yeah, we will see deflection. We will see when only electric field is present. Now I'll come to that. Next topic will be that only. So understand? Now there are some cases. Now particularly some cases is there. So you can see from the cases we should not be doing individually because this theta is 0. That means theta is 0 degree. That means the charge is going parallel to the direction of B.
Yes, sir.
So no force experience. If velocity is 0, that means one interesting fact. A moving charge particle, charge particle which is at rest in a magnetic field, is not going to experience any force.
In a magnetic field, not going to experience any force.
If it is at rest.
Okay.
If it has rest. But when it is moving with a velocity, when it is in motion, then definitely, if it is not parallel to the direction of magnetic field, it is going to definitely experience a force. And this force we will call it as Lorentz magnetic force. Now let us study more onto this Lorentz magnetic force. What is going to happen now? Okay? So now, first of all, continuing that. So there is something called velocity selector. Velocity selector. What is it?
Selector.
Velocity selector. You see, this is what used to be used in. This was what we used to use in this case of old televisions. Okay, CRT tubes. You see, we have a region. This is a region which contains capacitor plates, and also this is a region which contains a capacitor plate and also has magnetic fields. Magnetic fields being perpendicular to the plane of the an electric field, this plate to this plate. Okay, and a charge particle is passing through this one. So this is its trajectory. It will have three trajectories. One will be deflected like this. One will be deflected. Actually, the deflection not from there. It will be deflection will be from here only. I'll clean this. The deflection will be from either like this way or like this way. We would like to see which one is which one. Clear? So these are the two. So we know. So this is a charged particle. This is the velocity. So the total force experienced by the charge, by the positive charge, by the plus q charge will be what? F will be equals to QE plus Q V vector cross B vector, right? When only electric field is present, right? Only electric field is present. That means, that is, Fm equals to 0, then F will be only QE. So this being a positively charged plate, the electric field lines is coming from here to here. So that means this is plus, these are all plus, this is minus, 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 minus. That means positive plate is going to get attracted towards the negative plate only. So it will be taking this path. It will take path L2. right?
Yes, sir.
Now when if M is present, now when
Only
only magnetic field is present, only B is present, then what will happen? Fe will be 0. Fe 0 means F is equals to BQV sine theta. How I am writing this, you may be, if you remember, A cross B is written as AB sine theta, right?
yes, sir.
So that property I am using. So in this case, what will be the velocity? So V is this side, V is this side,
QV sine theta.
and cross means V cross B, yeah, up. So L1. So it will take the path which one? The particle will now follow which path? Particle will take L1. Right, will be deflected. So plus Q will get deflected, will get deflected along L1. Okay? Now for the particle to pass through the region undeflected, what we should do? F should be equals to 0. Net force acting on it should be 0. That means, that is, QE must be equal to BQV. Definitely theta is 90 degree always. So I am writing this because you can see this is the magnetic field and this is the charged particle. The angle between them is 90 degree only always. Going into the plane of the paper is the magnetic field and V is coming from left to right. That means it is always 90 only. So that means QE must be equal to BQV. So velocity of the charged particle must be E by V. So when the velocity of the charged particle is in this ratio, it will pass through the region undeflected and follow along which path? Hence it will follow along, let me name this as L.
Normal straight on.
So it will follow along L. Clear?
Yes, sir.
This is called velocity selector. This concept is called velocity selector. Okay?
Yes.
Got it? Okay then. So now, we have found this BQV sine theta, right?
Yes, sir.
So this is our Lorentz force done. So this is our introduction to Lorentz. Now let us see what is the motion of charged particle in magnetic field. What happens when it enters a magnetic field perpendicularly?
Pardon, sir?
Now let us see what will happen when the charged particle enters a magnetic field perpendicularly. So let us study motion of charged particle in magnetic field. So you see, if I have, so let's say this is any charged particle, this is any magnetic field which is perpendicular to the plane of the paper, right?
Sir.
This is any charged particle which is already present inside it. So a charged particle is already inside it. Now this is its velocity. So if I draw a circle,
Inside.
so we see that there is a charged particle here which is spinning in a circle. Why is it spinning in a circle? You can see this is the velocity vector
Yes.
Okay. Now the force which this force experiences, I want to explain you something. Let us explain like this way. Imagine the charged particle came like this. It penetrates into the magnetic field and then start moving in a circle. Why is it moving in a circle? This was its velocity vector, right? So we see, if we consider a charged particle, a positive charge plus q, moving with the velocity v, enters a magnetic field, uniform magnetic field at an angle. It is a magnetic field, enters a uniform magnetic field B perpendicularly. So as it enters perpendicularly, what do you see? So we can see the direction of the force, the direction of the Lorentz force, the direction of Fm, I'm just writing Fm, Lorentz force, is perpendicular to B and V. Okay? Correct? So in this case, this is velocity vector, the cross is the B vector, so you can hold it B cross V. You can see the Fm vector is always directed towards the inside. If you take another point here, let's say another point here, this is the velocity vector. Again you can see
that will be inside.
Directed inside. Again you can see it here, it will be directed inside. Okay? The direction of Fm is perpendicular to B and V is found to always directed towards what? Towards the circular path, directed towards the center, towards the center of a circular path, directed towards the center of a circular path. Hence, the charge particle, hence the charge plus q follows a circular path within the magnetic field the necessary centripetal force being provided by the Lorentz magnetic force, that is mv square by r, what is r is the radius of the circle, is equal to bqv. Why sine? Sine theta, sine is always 90 degree because velocity is perpendicular to magnetic field only. Okay? It is entering the magnetic field at 90 degree. I have said perpendicularly.
MVL.
BQV. mv square by r. Theta equals to 90. Okay? So I'll get here how much? mv square by r. V get cancel. I'll get here V equals to BQR by M. Okay, this is the velocity. This is the velocity of the world. But wait. Now, what is the kinetic energy? Kinetic energy of the plus Q of the charged particle would be what? Of the particle will be, kinetic energy of the particle will be how much? Half mv square. But m being the mass of the particle, so v would be, so half m b square q square r square by m square, right? So kinetic energy will be b square q square r square by 2m. This is the kinetic energy. Now one more thing. The angular velocity omega is equal to frequency by t, is equals to what I'm writing, theta by t, or we can write this as, that is theta by t, or we can write this as 2 pi by t, remember that. Okay, or we can write 2 pi nu, where nu equals to frequency and is given by 1 by time period. I'm giving you all the relations. In the upcoming chapters we're going to reuse all this. So I'm giving all the relations of angular velocity. Omega equals to 2 pi by t equals 2 pi nu equals to 1 by t, and so on. Correct? There's also one more relation. Relation between angular velocity and linear velocity is v equals to r omega. Okay? So that means omega equals to your v by r. Right? So I can write this omega equals to v by r. So v is how much I got? b q r by m into r. Cancel. So angular velocity is b q by m. Okay? b q by m. Now using this expression I can write 2 pi by t is equal to bq by m. So time period is equal to 2 pi m by bq. This is the time taken by the charged particle to complete one revolution. Okay? Time taken to complete one revolution. Okay? Taken to complete one revolution. What will be the frequency then? Frequency is equals to 1 by time period. That means it gives me what? Just let me check it once. Yeah. Yeah, done? Did it? So frequency would be equals to 1 by t is bq by 2 pi m. This is the frequency of oscillation. Now you can clearly see, if the charge to mass ratio, let me make a constant, let k equals to q by m, means charge to mass ratio, let's say. So you can see frequency is directly proportional to charge to mass, keeping everything constant, magnetic field being constant, 2 pi being constant. Frequency of oscillation is directly proportional to q by m, means the ratio. If the ratio is more, that is what I mean to say is that nu is directly proportional to k being the ratio I have named it. So now nu is directly proportional to k, means greater the charge to mass ratio, greater will be the frequency. So it's saying that if the mass of the charged particle is less, frequency will also be less if you go deep. Okay? Now example, to understand this situation, I'll give an example. Have you copied all this?
Yes, sir.
Now let me clean it. So what do I mean now is that, consider an alpha particle. This is an example to understand that, to elaborate the situation. Consider an alpha particle. and a alpha particle and a proton, okay, or a positive charge. Yeah, or a proton or alpha particle and a proton. Alpha particle is 4He2, that is his mass is alpha particle and positive charge. Let's say positive charge or proton, same thing, positive charge enters a magnetic field. A magnetic field, okay. Discuss the motion of the particles. Do not discuss, compare the motion. Compare the motion of the particles in the magnetic field.
Particles.
Compare the motion of the particles in the magnetic field. So here we have. So we will be discussing this. Here is a magnetic field. I see let's say a proton or a positive charge. It is entering. So this is alpha particle, and this is a proton which is entering this side. Okay, or positive charge. Now, which one do you think will describe more radius? Now, when they enter, you will see. So we have found out what is the radius. What are the radius of the what is the velocity? Okay. Considering alpha particle and positive charge entering a magnetic field with same velocity, with same v, compare the motion of the particle in the magnetic field. So please give me the expression for v. What I found out that time, v equals to how much? bq by 2m, no?
bqr by m.
bq by m. And bqr by m. Okay. So velocity is being same, but is the charge to mass ratio same? No.
No, sir.
Charge on alpha particle. So for an alpha particle it is 4He2. That is, charge on alpha particle is 2e. Okay. So Q1, which is the charge of alpha, Q alpha is 2e, and Q proton or positive charge is e. Okay. So now if I compare them, so their velocity being same, whose radius will be more? So what do you think will be the radius? R will be written as V into M by BQ, right?
Yes, sir.
Velocity being the same. Now which one is heavy also? Wait a minute. Mass of alpha particle and mass of our proton. Definitely mass of alpha particle is much larger. Much larger. Mass of alpha particle is greater than mass of proton, right? So how much is mass of alpha particle greater than? It will be generally provided to you. We can easily find it also. I think mass of alpha particle is 6 points. So mass of alpha will be 6 point something, no? Mass of alpha 6.6 into 10 to the minus 27 kg. Mass of alpha particle. Here is mass of alpha particle. Mass of alpha particle, yeah, 6.6. You see, into 10 to the minus 27. So mass of, let us do a side note. So mass of alpha is equal to 6.6 into 10 to the power minus 27, and that of mass of proton would be 1.2 into 10 to the power minus 27 kg, roughly. These are all rough work. So 6.6 divided by 1.2, that is 66 divided by 12. How much I get? So 66 divided by 10 is 6.6, and 66 divided by 2 is 33. No?
5.5.
So it should be how much?
5.5. 66 divided by 12.
Did you get 5.5?
Yes, sir.
Let's say that means approximately mass of alpha is 5 times of that of mass of proton. Okay? So then mass of alpha is 5 times of mass of proton. Let us compare the radius then. So this is R, we know. So radius of alpha by radius of proton will be what? V mass of alpha by B Q of alpha divided by V mass of proton by B Q of proton. So these two get cancelled, and I get here what? M alpha by MP is into QP by Q alpha. So mass of alpha is 5 times of that. So 5, this is M alpha by MP is 5 into, and Q alpha by QP will be equal to 2E by E, that gives me 2. Okay, so that gives me
2
half Q alpha, so that gives me 1 by 2 here. So R alpha would be half of, so R alpha, radius of the alpha would be half of RP. That means, so if the alpha, radius of half of P, okay, they are in the same velocity, so which one will have greater radii? Alpha or proton? Proton will have greater radii.
Yes, sir.
So when it enters, both of them being charged particle, this is the velocity, this is the velocity. So V cross. So can you do that? So this is V. So this is V going in. Yeah, actually it is coming out of the board. It is coming out of the board. Okay, because you see. Wait a minute. Cross going in. No, not coming out. They're going there. Sorry, going up. Going up. So that means this one will
dot across.
Will come out like this way. Okay, and what about this one? This one would be small. Its radius will be half of this. Exactly half. I just shown you. Okay, so this one will be going. We draw solid line only. Maybe this one is fast, that is later, doesn't matter. So here, this is the case. Okay. So whose radius will be more? Definitely alpha proton particle will be more. Similarly, you can compare for electron and a proton. Electron's mass is less. Okay. This is also explaining you that a light particle of high velocity will penetrate more into the magnetic field than the one which is quite heavy with the same velocity. Okay?
Penetrate more than the magnet.
Yeah, because it has covered a greater radius, na?
Yes, sir.
Okay, so imagine this kind of question, this type of question, maybe other charged particle will be compared. They may be asked that I gave you both alpha radius is given to you, that the radius of one is this time of that one. Which one will come out fast? Whose velocity will be more? So that means that will come out fast. So all compare based question like this will you will get it. Okay?
Yes, sir.
So now you can, the one part I am giving you from you to explore. Imagine the radius, what will happen if the velocities are different? If the velocities are different, compare their velocities now. If let's say the radius will not be same.
Yes, sir.
Take two alpha particles. One describe a greater radius and another describe a smaller radius. Let's say one radius is double the other, then whose velocity is more? Compare it.
Whose velocity?
will be more. Same charge particle, same to charge particle, but there, what is different?
Velocity.
Yeah. Velocity. One is entering at high speed, and there is entering at the low speed. So which one is that? I leave it for you to determine it. Okay.
So, but if the radius is same,
so
the radius will be double.
No. Give it so that one of radius is double the other. Then you do. Definitely we can see a relation. R and V, I can see one relation. Okay? Or maybe the charge, it may be also given. The two charged particles are entering a region in which charges are same but their masses are different.
Charges same, masses different.
So which one will have greater radii? You can clearly say that if V is constant, mass is different, right? Mass is same, charge is different. Definitely if charge is more, radius would be less.
Charge.
Don't write it. Compare from the equation and give this. Look at this. R is inversely proportional to Q. Q more or less, keeping every other factors constant. Okay?
Yes, sir.
Keeping every other constant. So, this is it. Okay?
Yes, sir.
So we have done this. Now, I'll stop here today. Okay?
Okay, sir. Yes, sir.